one and all. I welcome all the MPCS second year students to the online classes. The summary of last lecture that we have discussed about Young's double slit experiment. During the last class, I have derived condition for bright fringes, condition for dark fringes. This is a continuation topic of our previous class. In the previous class, we have derived these two equations, that is r sin theta is equal to a2 sin delta and r cos theta is equal to a1 plus a2 cos delta. These are the two equations which we have derived in our previous lecture. So from these two equations we can calculate the resultant phase of the two waves. What is resultant phase? Theta. Capital R, resultant amplitude. A1, A2 are amplitudes of the individual waves. Delta is the phase difference between the two waves when they are not superimposed on each other. After superimposing, after overlapping on each other, the resultant phase is represented by theta. Clear? Right. Here I want to calculate theta value individually. So resultant phase of the two waves after overlapping. This can be calculated from these two equations. Just divide this equation by the second equation. Simply I am dividing these two equations. R sin theta by R cos theta. I have taken LHS. I have divided the first equation by second equation. Coming to the right hand side, A2 sin delta whole divided by A1 plus A2 cos delta. 1R gets cancelled. Sin by cos becomes tan. Tan theta is equal to A2 sin delta whole divided by A1 plus A2 cos delta. So I want to calculate theta value individually. Therefore, resultant phase of the two waves after overlapping is equal to, just to take this tan from LHS to RHS, it becomes a tan inverse of A2 sin delta whole divided by A1 plus A2 cos delta. This is the final expression. So from Young's double slit experiment, I have derived three cases. One is what is the condition to get bright fringes? When we get bright fringes, when phase difference is equal to n lambda. Phase difference is equal to, I have calculated in terms of phase difference and in terms of path difference. What is the path difference between the two waves to get bright fringes? That is n lambda. When the two individual waves, if they are having this much of path difference, after superposition between them, we get a bright fringe. When we get dark fringe, when path difference is equal to 2n plus 1 into lambda by 2. These are the two conditions to get bright fringes and dark fringes due to two waves. This is the third case. This is the first case. This is the second case. This is the third case. What is third case? Resultant phase of the two interfering waves. So with this topic, our Young's double slit experiment will be over. And these two expressions are very, very important. So in next topics, we will use these formulas and we will derive final expressions in those topics. So you have to remember these expressions directly. Clear? Right. Our next topic is about fringe width. What is fringe width? In the previous class only I have explained about fringe width. After forming interference fringes, we can calculate fringe width. The distance between the successive bright fringes or successive dark fringes is called fringe width. Generally, interfering fringes consisting of bright and dark fringes like this. The distance between the successive bright fringe or dark fringes is called fringe width. Here I am going to derive formula for fringe width, that is beta. This is the actually continuation topic of Young's double slit experiment only. By using Young's double slit experiment only, we can calculate this fringe width. So our next topic is fringe width, and that is represented by beta. Listen carefully. To derive expression for fringe width, again we have to remember the experimental arrangement by Young double slit experiment consisting of a monochromatic source of light. This is monochromatic source of light. These are the two slits, S1 and S2, and these two slits are separated by 2D distance, and this is the position of the screen. This is the position of the screen. Clear? Right? Let the distance between the slits to the screen be capital D. These terms are very important, standard terms. Capital D is the distance between the slits and the screen. This is the position of the screen. And 2D is the distance between the two slits. So let O be the one point on the screen. O is the center of the screen. Clear? Here I am considering one point, that is P. P is one point. Let us imagine the wave coming from S1 reaching P. Simultaneously the wave coming from S2 also reaching point P. And these two waves are superimposing on each other, forming a fringe on the screen at a point P. Maybe it is bright fringe or dark fringe. See, the distance between the center of the screen and point P on the screen, here I am representing by X. Let this point be situated at X distance from the center of screen, and C. Right? Let this point be some Q. This point here I am representing as R. See the diagram carefully. What is the distance between the two slits? S1, S2 are two slits which are separated by how much distance? 2D. If this distance is 2D, this distance will be small d. This distance will be small d, and this distance is also small d. D plus d, again we get how much? 2d. Clear? Right. Just to see the diagram carefully from figure. Right? Just consider a triangle, that is triangle S1PQ. See the diagram carefully. S1PQ. It is a right angled triangle. Right angled triangle. So when we have right angled triangle, we can apply Pythagoras theorem. What is Pythagoras theorem? Hypotenuse square is equal to, what is hypotenuse of this right angled triangle? S1P is equal to base square. What is base? That is SQ plus height square. Height of this right angled triangle PQ. Clear? Let this is equation number 1. Similarly, here I am considering second right angle triangle, that is S2PR. This is also a right angle triangle. S2 from S2 triangle S2PR. This is also right angle triangle. You can apply Pythagoras theorem for this right angle also. So S2P whole square is equal to hypotenuse square is equal to base square, that is SR square plus height square PR square. Clear? Right. So see the diagram carefully. Let this be equation number 2. I want to substitute the values of SQ, PQ and S1P. See, for equation 1 also can be written as S1P whole square is equal to, what is SQ value? S1Q value. S1Q value, this distance. This distance is equal to the distance between the slits to the screen. So S1Q can be represented by D, since here we are having S1Q square, so it becomes D square plus PQ square. This one, how do we calculate PQ value? This distance, this total distance is X value, and this distance already small d, but I want to calculate PQ value. How do we calculate PQ value? Total distance X minus small d gives what? PQ value. Instead of PQ, you can replace as X minus small d, but here we are having square X minus d whole square. I am giving number for this equation. Coming to the second right angle triangle, this one, S2P whole square is equal to S2R, this one, S2R. S2R is also equal to capital D only, that is the distance between the slits to the screen, plus PR. See the diagram carefully. From P2 R equal to how much distance? This distance is already X. From this diagram, this distance is equal to small d. So PR is equal to X plus small d. So instead of PR, you can replace as X plus small d whole square. Clear? Right. Let this is equation number 2. So just to subtract equation 1 from equation 2. Simply I am subtracting equation 1 from equation 2. So what is equation 2? We have to write first equation 2 only. What is the LHS of equation 2? This one. S2P whole square minus, what is LHS of equation 1? S1P whole square. Coming to the right hand side, what is the RHS of equation 2? This one, capital D square plus X plus small d whole square minus this equation minus this one, minus D square. See the equation 1, minus D square minus X minus D whole square. This plus capital D square minus capital D square gets cancelled. So this can be written as S2P whole square minus S1P whole square is equal to X plus D. X plus D whole square can be expanded as, this is in the form of A plus B whole square. A square plus B square plus 2AB minus of, this is A minus B whole square. So again A square plus B square means D square minus 2XD. Is that clear? Right. So this is in the form of A square minus B square, can be written as A plus B into A minus B, that is S2P plus S1P minus into S2P minus S1P. I am using A plus B into A minus B formula. Clear? Coming to the right hand side, x square plus d square plus 2xd minus into plus minus. So all terms, so the signs of all terms in the bracket will be reversed. Plus becomes a minus, this plus side becomes a minus, this minus side becomes minus into minus plus. Last term becomes a plus. Clear? This is 2xd. Is it clear? Just to follow the derivation. This plus x square minus x square gets cancelled. Plus d square minus d square gets cancelled. 2xd. These two terms will be added. So next step will be S2P plus S1P into S2P minus S1P, which equal to 4xd. Let this is equation number 3. See the diagram carefully. When capital D is very greater than small d, to get the final expression, remember, here I am making one important statement. Just you have to keep this point in your mind. To get the final expression only I am doing like this. If you compare capital D distance with this small d distance, capital D distance is very large when compared to small d distance. So when capital D is this is very high value when compared to small d. In such a case, these two waves, these two light rays travel equal distances. That means S2P is equal to S1P. See, imagine like that, like this. Just to imagine this screen is moving like this. When screen is moving in forward direction, the distances are traveled by these two waves so nearly going to be equal, like this. Finally, they become equal. This is a condition which we are assuming to get the final expression. So in this case, S2P approximately equal to S1P. That is equal to, when this screen is moving in forward direction, so S2P or S1P becomes how much? Capital D only. That is the distance between the slips to the screen. So this is the condition, very important condition. To derive the final expression, I am assuming this case. And remember, be careful. If you substitute these values as it is in this expression, you will get 0. You have to substitute S2P and S1P as D in this value only. If you substitute here, it is going to be 0. The whole value becomes 0. Clear? But we have to substitute this S2P and S1P as capital D in this bracket only. So simply I am replacing these two values, that is capital D plus capital D into S2P minus S1P, which is equal to how much? 4xp. D plus D becomes 2D. 2D into S2P minus S1P. What is S2P minus S1P? S2P is the distance traveled by the second wave from switch to the screen. S1P is the distance traveled by the first wave from slit to the screen. So S2P minus S1P gives, that is the path difference, distance difference traveled by the two waves. That I want to calculate here, which is equal to 4xd. I want to calculate S2P minus S1P only. So our next step will be S2P minus S1P, which is equal to 4xd by 2 capital D. Clear? 2 1 ja 2 2 ja. So S2P minus S1P, which is equal to 2xd by capital D. Let this is equation number 4. Okay? Right. What is S2P minus S1P? That is the path difference between the second wave and first wave. for bright fringes. I'm going to derive expression for fringe width beta with respect to bright fringes. I will derive the same expression for beta with respect to dark fringes also. So both expressions will be same. So we have to derive we have to follow both the procedures. Right. Just to remember the previous class. Condition for bright fringes. Since condition for bright fringes, just now only I have explained. When we get bright fringes, when path difference between the two waves is equal to n lambda, we get bright fringes. This is the path difference. So path difference between the two waves, these two waves. Path difference between the two waves, that is S2p minus S1p, is equal to n lambda. We get bright fringes. See the equations 4 and 5. 4 and 5, LHS of equation 4 and LHS of equation 5 are equal. You can equate RHS. So from equations 4 and 5, simply I am equating RHS of equation 4 to RHS of equation 5. Clear? Right. Then our next step will be x is equal to, I want to calculate x. What is x? That is the distance of the point P. Maybe it is bright fringe. According to our case, the fringe formed at point P becomes bright fringe. So the distance of this point bright fringe from center of the screen I want to calculate. Clear? So the next step will be x is equal to just take capital D from LHS to RHS, it will comes in the numerator, and this 2D will come in the denominator. Our expression becomes n lambda capital D whole divided by 2D. Let me see equation number 6. Just give the numbers for this n. What is n? The n represent, here in this particular case, n represents, that is the number of bright fringes from the center of screen, right? When n is equal to 1, represents, that is the first bright fringe from the center of the screen, this one. This distance, first bright fringe, maybe this is second bright fringe, maybe this is third bright fringe. Is that clear? Right. So I want to write a distance for first bright fringe. By using this equation, you can write when n equal to 1, let put x as x1 is equal to, instead of n I am writing as 1. So this equation becomes lambda capital D by 2 small d. Let this equation number 2. When n is equal to 2, that is the distance of the second bright fringe from the center of the screen. That I am representing, this distance I am representing as x2. This distance I am representing as x1. Already I have derived x1. So from equation 6 again we can write x2 is equal to, instead of n you can write as 2 lambda d by 2d. What are equations 7 and 8? Equations 7 and 8 are the bright fringes, successive bright fringes from the center of the screen. This is the first bright fringe x1, this is x1, and this distance is x2. This is the second bright fringe. If you subtract x1 from x2, you will get the distance between the successive bright fringe. That is nothing but fringe width. So simply I am subtracting x1 from x2, so that you will get beta value. See, beta is equal to x2 minus x1. Just remember, what is the definition for beta? The distance between the successive bright fringes is called fringe width. This is equation number 9. So beta is equal to, what is x2 value? 2. Simply I am substituting x1 and x2 value in equation number 9. 2 lambda d by 2d minus lambda capital D by 2D. So LCM will be 2D only. So 2 lambda capital D minus lambda D. It comes out as lambda D by 2D. This is a final expression for fringe width. I have derived expression for fringe width, that is beta, by using condition for bright fringe. We can calculate the same expression by using condition for dark fringe. Just see. Here I am going to derive one more derivation for beta, but with respect to dark fringe. That I am doing here. Just to listen carefully. So you have to remember the final expressions, that is beta expressions. Right. I want to derive the same expression for beta, but by using condition for dark fringe. What is the condition for dark fringe? Condition for dark fringe. When path difference is equal to, when path difference, that is the path difference between the first and second waves is equal to 2n plus 1 into lambda by 2, we get dark fringe. We have to remember these expressions, these conditions directly. Without these general conditions, we cannot derive expression for beta. Clear? Right. So this is a case I have derived in the previous class. Let this is the equation number 11. Just substitute equation 4 in 11. Just substitute equation 4 in equation 11. Right? So what is equation 4? This one, instead of s2 minus s1, you can write as 2x small d instead of this value. 2x small d whole divided by capital D. 2n plus 1 into lambda by 2. Every time I am calculating x value. By using this case also I have calculated x value. After giving n values for n as 1 and 2, I can calculate beta value. Similarly, during this derivation also we have to calculate x value. So x is equal to transpose, just 2d comes in the denominator, capital D goes into the numerator. So expression becomes 2n plus 1 into lambda capital D whole divided by, this is 2d, this is already 2, becomes 4 into small d. Clear? Let this equation number 12. Just give the number for n values. When n is equal to 1, what is this meaning? When n is equal to 1, that is the distance of the first dark fringe from the center of the screen. That is, x becomes x1, n is equal to 1. 1 into 2 becomes 2 only. 2 plus 1 becomes 3. 3 lambda capital D by 4. Similarly, when n is equal to 2, x becomes x2, n equal to 2, 2 2s are 4. 4 plus 1, 5. 5 lambda capital D by 2D. Let this is equation number 13. Let this is equation number 14. I have derived equations for first dark fringe and second dark fringe from the center of the screen. Just to subtract equation 13 from equation 14, you will get beta again. What is beta? That is the distance between the successive dark fringes, also called as beta. This is distance between the successive bright fringes, is also called beta, fringe width. Clear? I am doing the same derivation like bright fringes. So beta is equal to, what is x2 value? This one 5 lambda capital D by 2D. What is x1 value? 3 lambda capital D by 4D. This is already 4. This is also 4D, not 2D, 4D. So LCM will be 4D only. So 5 lambda capital D minus 3 lambda capital D becomes how much? 2 lambda capital D by 4D. 2 1 ja 2 2 za. So final expression for beta, that is beta is equal how much? Lambda capital D by 2D. This is the expression for fringe width, but with respect to dark fringes. This is with respect to bright fringes. Clear? Right. So this is about derivation of fringe width in case of interfering fringes. What is the definition for fringe width? The distance between the successive bright fringes or successive dark fringes is called fringe width. So expression for fringe width is equal to lambda capital D whole divided by 2D. Capital D is the distance between the slits to the screen and 2D is the distance between the slits. Clear? Right. This is about fringe width. Our next topic is about coherence. Listen carefully. A very important concept. 4 marks question. Just concentrate. Our next topic is very important for 4 marks. That is coherence. This is one phenomenon. Coherence. What is coherence? When two or more waves having same phase or a constant phase difference, then the two waves are said to be coherent sources, and that phenomenon is known as coherence. That means having same phase between the sources is known as coherence, and the sources which are emitting the waves having same phase difference are known as what? Coherent sources. How do we define coherence? It is a phenomenon. It is a phenomenon having same phase or constant phase difference between the two sources of light is known as coherence. And phase means what? Let this is first wave and this is the second wave. Imaginary. And these two waves are progressing in forward direction. Then what is the question? That phase difference between the first wave and second wave. How much phase difference between these two waves? See, this second wave is 180 degrees lagged by the first wave. In other words, first wave is 180 degrees ahead of second wave. This is actually 180 degrees. Clear? So what is the phase difference? These two particles, this one and this one, exactly 180 degrees. So this is about phase difference. If throughout the motion, if they are maintaining same phase, that phase difference, these two waves can superimpose on each other and they can form interfering fringes. Or if the two waves are in same phase also, crest, trough, they are in same phase. There is no phase difference between these two waves. Same phase also, they can form interfering fringes. So the sources which are used to generate these type of waves are known as what? Coherent sources, and this phenomenon is known as what? Coherence. Clear? Right. This coherence again divided into two types. First one is spatial coherence. Second one is temporal coherence. Types of coherence. Again I am defining coherence. What is coherence? When two waves which are having same phase or constant phase difference, then the sources which are helping to generate that type of waves are known as coherent sources, and that phenomenon is known as coherence. And depending on that phase, the coherence are classified into two types: spatial coherence and temporal coherence. What is spatial coherence? When phase difference between the two waves do not change with respect to time. When the phase is not changing with respect to time, that type of coherence is known as what? Spatial coherence. Clear? Right. Coming to during this coherence, phase difference is constant. Coming to temporal coherence. What is a temporal coherence? Temporal coherence means, see, this is the wave I am considering. I want to extend the distance traveled by the wave. How do we increase the distance traveled by the wave? Simply by introducing a transparent sheet like mica, right? When a transparent sheet is introduced in the path of wave, the distance traveled by the wave will be increases. So the contrast of the wave will be decreases. In such case, we say the temporal coherence is lost by the wave. When we say temporal coherence lost by the given wave, when its contrast decreases. When contrast of the given wave decreases, when a transparent sheet like mica is placed in the path of the wave, its contrast will be lost. In such case, we can say the temporal coherence is losing by the wave. When a sufficient thickness of the transparent sheet is placed in the path of wave, what happens? The total wave will be stopped. That means the total contrast will be disappears. In such case, we say the given wave lost completely temporal coherence. This is about temporal coherence. This is about spatial coherence. This is a very important question for 4 marks. Number of times this question came in the annual examination. Tomorrow we will discuss a new topic. Until then, bye bye.